Hello everyone, so welcome you to this course on optimization algorithms, theory and software implementation, and yeah, this is the first lecture. So in the first two lectures, we will rapidly cover the basics of optimization theory. I will start with certain applications of optimization to have a head start. Okay. When we start with optimization, one always has this particular question, right. So, yeah, why optimization and what are the applications to optimization, right. Um yeah, I am not sure if you would be surprised when I say that optimization is actually being used in everyday life by every person whom you can see. Okay. Why do I say so? Consider the following problem, okay, so which I call as the problem of time management. Okay. So, any family man, okay, has a lot of things to do on a day to day basis. So, he has to do it every day. He has to work in the office for about 8 hours. He has to, let us say, attend a meeting for about 1 or 2 hours. So, other than that, he has to run around to buy groceries and medicines for his family members. He has to prepare for the next day meetings. He also has to spend certain time with his family, and he also needs to have his food, do his other daily chores, and also have a sound sleep for at least 6 hours, right. So, that is quite a bit of things to do on a day to day basis, right. So, but to finish all this, he only has 24 hours, right. So, he cannot ask saying that, yeah, it is a very hectic day, give me more time, right. So, he has to split 24 hours in such a way that he completes all of these tasks and also maximizes his happiness out of whatever he does, right. So, let me actually model this as an optimization problem. Okay. So, as an example, let me say that T1 is the time in hours. Okay. So, all of this is in hours, time spent for office work. Okay. T2 is the time spent on meetings. T3 is, say, time spent with the family. So on, and let us say Tn is sleep time. Okay. And let us consider that he gets a utility of u1 of T1 for the times based on the time spent on office work, and u2 of T2 for the time spent on meetings, and so on, and un of Tn for his sleep time, right. So, what does he want to do? He likes to maximize u1 of T1 plus u2 of T2 plus un of Tn, subject to the constraint that T1 plus T2 plus dot 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 plus Tn is equal to 24. So, this maximization is over T1 to Tn. Okay. So, you can see that this is actually an optimization problem where he has to maximize the sum of utilities, okay, subject to the constraint that he has exactly 24 hours in a day. Okay. So, every one of us who is managing time on a daily day-to-day basis, right, is actually solving this particular time management problem, right. So, that is why I said optimization problem is actually being solved by every person on a day-to-day basis. Okay. You might actually ask me whether someone actually thinks whether, okay, what is his utility here, what is his utility there, and so on, right. Yeah, he may not do it every day thinking, I mean calculating the utilities exactly and finding the optimal amount of time and so on, but yeah, if you see what are his activities over let us say a few months or a year, okay, you can actually see that he would have spent more amount of time for the task that gives him the highest utility, okay, and the next amount of time for the task that gives him the next highest utility and so on, right. So, yeah, this is a problem that every person is actually solving, so that he actually manages his time effectively every day. Okay. So, fine. So, that is a more layman kind of an example. We will look at some examples that are used in the academics. Okay. So, one of the key problems that economists solve is what we call the utility maximization problem. Okay. So, yeah, let us consider the utility maximization problem that is well known in economics. So, we have a consumer having an income of W. Okay. So, let us assume that so he wants to buy many items as much as possible with his income. So, let us say there are n items and x1 is the quantity of item 1 that he buys, x2 is the quantity of item 2 that he likes to buy, dot 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 xn is the quantity of item n. Okay. So, and he actually gets a utility of x1, x2 dot 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 xn when he buys a quantity of x1 amount of item 1, x2 amount of item 2 dot dot xn amount of item n. Okay. So, he buys x1, x2 dot 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 xn in such a way that the budget constraint is satisfied. Okay. And the other constraint that needs to be satisfied is that every quantity needs to be non negative. So, here the variables P1, P2 dot 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 Pn refers to the price of item 1, item 2 dot 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 item n. Okay. So, maybe I will write that down as well. So, P1 is price of item 1, P2 is price of item 2 dot 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 Pn is price of item n. Okay. So, this as you can see is another popular optimization problem, where the consumer maximizes his utility subject to the budget constraint and the non negativity constraint on the quantity of the items. Okay. So, yeah, this is another popular optimization problem, and another popular optimization problem is something in data science. Some of you might have heard of this term called as the support vector machine. Okay. So, in short we call it the SVM. Okay. I am not going to elaborate what is a support vector machine, but I will tell you what we are expected to do in a support vector machine. Okay. So, let us consider that we have a training data. Okay. So, a training data set which is represented as x1 y1, x2 y2 dot 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 xn yn, where x1 x2 dot 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 xn represents the features and y1 y2 dot 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 yn represent the labels. Okay. So, that is for each data point. X1 is a data point for which there is a particular label, x2 is a data point for which there is a particular label, dot 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 xn is a data point for which there is another particular label, right. And yeah, so we consider a binary classification problem. So, yeah, yi is either -1 or +1. Okay. So, given this setup, what do we want to do? We want to solve the following optimization problem, which is min half norm w squared, okay, subject to the constraint that yi into w transpose xi plus b is greater than or equal to 1 for all I equal to 1 to n. Okay. So, just to give you an understanding of what this optimization problem does. Okay. So, when you are given a separable data set, okay. So, for example, let us say I will consider that x1 x2 dot dot xn are in 2 dimensions, features in 2 dimensions. Okay. So, let us say yeah, I will draw those that are labeled as -1 in red. So, let us say yeah, these are the points, okay, and those that are labeled as +1 I will draw it in black. So, okay. So, what SVM does is it actually separates, finds the best separator between the set of points that are labeled as -1 and the set of points that are labeled as +1. Okay. So, note that there are many possible lines that can be drawn. Okay. So, for example, we can draw this line. Okay. So, that is one possibility. Okay. We can draw this line, that is another possibility. We can draw this line, that is another possibility. Okay. So, just by looking at the figure, you see that somehow the one that I drew in thick black, right. So, that seems to be the best separator rather than the others, right. So, such a best separator is actually found using support vector machines by solving this optimization problem whatever we have written here. So, B is a scalar and W is a vector of size equal to the size of the vector xi. Okay. So, yeah, these are some different examples of optimization, and you can see that at this point we have actually seen examples from day to day life, from any layman's life, and also from those that involve academic interests, say from economic sciences and also from data analysis, right. So, if you see the problems, they are of the following form. Okay. So, in each of the problems, okay, I am actually minimizing some function, let us say f of x. So, let me write it as f of x1 to xn, okay, subject to the condition that x, which is written as an n tuple, okay, this actually belongs to some constraint set S. Okay. So, whenever we have a problem of this sort, okay, so it is an optimization problem. Okay. You can see that f is some function from R n to R, okay, and throughout the course we assume that this function is twice differentiable. Okay. So, given that we have got the applications right at this point of time, we will go into the theory as fast as possible. So, as far as optimization is concerned, there is a broad classification which we call as unconstrained optimization and constrained optimization. Okay. So, optimization can be broadly classified as unconstrained and constrained. So, to explain mathematically what is the difference. So, we call the problem unconstrained if S is actually equal to R n. So, this set what we have defined here, right. So, we want the set of x1 to xn to belong to some set if the set is actually R n, that is it can take any real value, x1 can take any real value, x2 can take any real value dot xn can take any real value, then I call such an optimization problem as unconstrained. And if S is not equal to R n, then there is a constraint on what values of what values x1 to xn can take, and such an optimization problem is called as a constrained optimization problem. Okay. So, as far as algorithms are concerned, again we would separate it as algorithms for unconstrained optimization and algorithms for constrained optimization. Okay. So, that is a very broad classification. So, we will now understand more about the solutions of an optimization problem. Okay. So, yeah, let us consider this problem of minimizing f of x subject to x in S. Okay. So, when do I call a particular point x star as a solution? Okay. So, again in solution there are two kinds of solution concepts. Okay. So, yeah, as far as solution concepts are concerned, a solution can either be a global solution or a local solution. So, what is the definition of a global solution? So, X star is a global solution of the above optimization problem if f of x star is less than equals f of y for all y in S. Okay. So, yeah, so this is when we call x star is a global solution, and yeah, it is a local solution if f of x star less than or equal to f of y for all y such that okay. So, what this means is that look at a ball around x star and you verify whether within that ball yeah, f of x star is less than or equal to f of y. Okay. So, yeah, the ball must also intersect with the set S. Okay. So, it is easy to see that every global solution should also be a local solution. Okay. But the reverse is not true. So, which means local solution is a weaker concept and global solution is yeah, a stronger condition that needs to be satisfied. Okay. Yeah, to give you some examples on global solution and local solution. Okay. So, we can have optimization problems where there are no global solutions or no local solutions. Okay. As an example, so let us say we have f of x equal to x. Okay. So, if you plot this, I mean plotting is an easy way to identify. So, we are actually trying to solve the problem min f of x subject to no conditions, that is subject to x in R. Okay. So, let us say f of x equal to x. You can see that yeah, the minimum does not exist or yeah, in layman's language the minimum is at minus infinity, right, but minus infinity is not a part of R, right. So, we say that a minimizer as a solution does not exist. Okay. So, this is an example where neither a local solution exists nor a global solution exists. Okay. So, here is another example where a local solution exists, but a global solution does not exist. Okay. So, let us say f of x equal to x minus 1 into x plus 1. Okay. So, yeah, this is like this, right. So, you can see that there is no global minimum, but you have a local minimum at x is equal to half. Okay. So, this is a case when local min exists, global min does not. Okay. So, here yeah, neither local min nor global min exists. Okay. And so, let us say yeah, let us take other possibilities where both local min and global min exists. Okay. So, yeah, the nicest example is where where x is equal to 0 is both local min as well as the global min, right. So, yeah, both local and global min exists, and local min equal to global min. Okay. And finally, so let us actually see an example where both local min and global min exists, but you have a local min which is not a global min. Okay. So, let us take this example. Okay. So, here you have -2, -1, 0 and 2. Okay. So, here you can see that there are 2 local minima, okay, of which one of them is global minimum, but the other is only a local minimum. Okay. So, this is only a local min. So, this is actually the global min. So, you have an example where you have both local min and global min for a function, but local min is there is a local min which is actually not a global minimum, right. So, these are certain examples to illustrate the differences between the local minimum and the global minimum. So, in the next lecture we will actually look at conditions where local minimum and the global minimum will be one and the same. Thank you.